Let's do some more problems. In problem 3, in section 3.3, problem number 8. We have a car driving around a circular track, which is weird, but fine. Car driving around a circular track. The circumference of the track is 1.5 miles. So 1.5 miles is equal to 1 lap. We want to have a linear speed of 75 miles per hour for 20 minutes, and we want to know the number of laps we need to make. So we've got a time and a linear speed. From that, we can get a distance. We can get a distance in miles, and then we can take our distance in miles and convert that to a number of laps. All right, so there's our plan. We're going to take our linear speed and our time and combine those to get a distance. So 20 minutes is not as useful of a time because our linear speed is 75 miles per hour. So I want to take I can either take my 75 miles per hour and convert it into miles per minute, or I can take my 20 minutes and convert it into an hour or into hours. I think I'll just convert minutes into hours. Because once again, it's 3.5 miles. If it's driving, it's 26,000 feet if it's a mountain. So I don't know, 75 miles an hour seems like something we should keep and convert the minutes, make the minutes fit the hours. Otherwise, our miles per hour will become miles per minute or MPM. That's weird. So we're going to take our 20 minutes and say there are 60 minutes in 1 hour. So our time is 1/3 of an hour. Now I have a unit match between my linear speed and my time, and I want to find a distance. Distance is equal to rate times time. So now we're going to switch to distance is equal to rate times time. Our rate is 75 miles per hour. And our time is 1/3 of an hour. $75 divided by 3 means we're driving a distance of 25 miles. But the number that we're looking for is not how far we went, it's how many laps we do. 1.5 miles is equal to 1 lap. So I want to convert my 25 miles into laps. So if 1.5 miles is 1 lap, then 25 miles, and we ought to figure out 25 miles is some other number of laps. So what we can do is take our 25 miles and we'll note that there are 1.5 miles in 1 lap. And take a 25 and divide it by 1.5. So we get 16.667. We look at our selection of answers and see that it's in fractions and not decimals. So we'll just have our calculator convert it to 50/3. So it's 16 and so 25 divided by 1.5, it's 16.667. So if I subtract off the 16 and then hit math, the first selection is fraction. And it says convert this to a fraction. And it says it's 2/3. So 16 2/3 laps. So second, or just press the math button. You don't have to press second. And it's the first selection in the math menu. Any questions? Cool. There are other things we could have calculated, but we didn't need them in this case. We had a circumference of 1.5 miles. So kind of raises the question about what's the radius of this track. So 1.5, if I divide that by 2 pi, the radius of the track is 0.23 miles. That's not really helpful. I don't have a frame of reference for a quarter of a mile as a radius for a track. So I guess we'll just have to let that one go. We had a similar question in the review, problem number 2. We have a bicycle with tires of radius 17 inches. So a radius of 17 inches is being ridden by a boy at a constant speed. The tires are making 6 rotations per second. So our angular speed is 6 rotations per second. How many miles will he ride in 40 minutes? Time equals 40 minutes. And we're reminded that 1 mile is 5,280 feet because great system. And we want to answer in miles. So I'm going to make a note of the answer to make sure we land on it. 24.3 miles. So this is similar to the problem that we had a couple of problems ago. We have a radius, we have an angular speed, we have an amount of time. So we can figure out how many radians we go through, and we can convert radians to linear distance with multiplication. But we've got some problems. Our angular speed is 6 rotations per second. We got to figure out how many radians per second that is. So 6 rotations per second, how many radians per second is that? So yeah, we'll take 6 rotations per second. 1 rotation is 2 pi radians. So we'll get 12 pi radians per second. We're going to do 12 pi radians per second times 40 minutes. Our angular speed multiplied by time will give us an angle. So once again, we're going to go back to our omega is theta over t, or if we want theta, we just do omega times t, but we got to make sure omega and t agree on what scale we're going to use. So our omega is 12 pi radians per second. Our time is 40 minutes. Oops. The wrong way. Oh, we want to multiply by 40 minutes, but I'm still going to be left with minutes. So I do omega times time, but my minutes are all messed up. So I have to say that 1 minute is 60 seconds. So now the minutes will cancel out, our seconds will cancel out, and we'll be left with radians. This will give us a theta. We can do this in whatever order is convenient to us. So I could do the 12 times the 40 and then take the result times 60. Or I could do the 12 times the 60 and multiply by 40, or 40 times 60 and multiply by 12. Since I have a calculator, it doesn't really matter. 12, 40, 60, 28,800 pi. Now that I have an angle, I can combine that with a radius to get a distance or an arc length. So S is theta times R. So theta is 28,800 pi times 17 is a radius. $489,600 pi inches. So let's just do the same thing we did before. We'll multiply by pi to get the actual number of inches. Then we'll divide inches into feet. So divide by 12. And then we'll remind ourselves that we're looking for miles. So we'll divide this by 5,280 and cut this down to 24.3 miles. I had to go from inches to feet and then from feet to miles because I can't remember how many inches there are in a mile. So I just do it in stages, 2 stages. Then, of course, we would want to divide this by 26.2 to find out the number of marathons we'll be doing. So this is clearly 0.926 marathons. I'm just kidding, no one uses marathon. Multiply by 2, and it's 1.85 half marathons. That would be an even more ridiculous. I think I'm in favor of it. But before that, we'll convert it to minivans. Any question? Is everybody okay? And we look so very sad. Have we just realized that this is the end of week 6, and so we're just like a third of the way down? Yeah, 17 weeks, we've done 6. So more than a third. Well, I remember this problem. This problem just seems mean. A ladybug is clinging to the outer edge of a child spinning disc.
What?
I like in the previous question. In the previous question, for some reason, it had to be a boy riding the bicycle, not a child riding the bicycle. In this one, they just say child. This is obviously a boy doing this because only a boy would have the spinning disc with a ladybug on it. I know, and it's just they just have to. It's a ladybug. Oh, it's a problem with a ladybug, and you're like, oh yay! And it's like, oh, clinging to the edge of a disc. I'm like, oh, ah! Someone take this child's spinning. Why does this child have a spinning disc? Also, I don't even know. The disc is 6 inches in diameter, so it's smaller than a frisbee. Is it a CD? Did he put a 6-inch diameter wheel on top of a fidget spinner? It's going at 30 revolutions per minute. How fast is a ladybug traveling? Too fast. How about that? Too fast. The answer is 2 for too fast.
Why? That's a lot of.
That's a lot of radians. Yeah. All right. All right. That's fine. Let's write down our information. Poor little bug. This kid needs someone to explain some stuff to him. Jeez. So the radius is 6. The diameter is 6 inches. So the diameter is 6 inches, so the radius is 3 inches, and our angular momentum or angular speed is 30 revolutions per minute. Yeah, diameter is 6, so radius is 3. And we got 30 revolutions per minute. How fast is the ladybug traveling? So what is the linear speed? Apparently 565 inches per minute. Let's make a note of that. That's a weird speed, inches per minute, but that's fine. America. All right. So we've got some calculations to do. We've got an angular speed in revolutions per minute. If it's 30 revolutions per minute, how do I turn that into radians per minute? Multiply by 2 pi. So I'll take my 30 revolutions per minute and multiply by 2 pi radians per 1 revolution. So that's going to be 60 pi radians per minute. That's our omega, our angular speed. If I want to convert our angular speed to linear speed, we just multiply our angle by our radius. So our linear speed we'll take our 60 pi radians per minute and multiply by 3 inches, and we'll have 180 pi inches per minute. We are to answer in multiples of pi, so we'll take our 180 and multiply by pi. And we get the 565 inches per minute. But that's a good question. So if it's 565 inches per minute, if we divide this by 12, that'll give us 47.12 feet per minute. And if I divide that by 5,280, that'll give us 0.008924 miles per minute. So if I multiply that by 60, we get 0.535 miles per hour. Okay, that's not so bad. So we just take the 565 divided by 12 to get feet, divided by 5,280 to get miles, but then multiply by 60 to get from minutes to hours. Maybe the ladybug is entertained because it's only like a half a mile an hour. I don't think that the ladybug is playing at only a half a mile an hour. How fast is that relative to, say, your walking speed? What's your walking speed? About 3 miles per hour. Like kind of a lazy pace. So I can imagine if I'm walking at 3 miles per hour, I can imagine a ladybug just hanging out on my shoulder without too much trouble. And this would be going at 1/6 of that speed. Yeah, this ladybug isn't thinking, he's just standing on a circle. If this kid is trying to fling the ladybug off the spinning circle, he's not doing a good job. And the ladybug is flipping him off. I was taken in by this 30 revolutions per minute because that seems pretty fast, but it's just not that fast because it's not. Now, if this was like a 3-foot radius, that would be going much faster. Maybe this kid is just modeling one of those problems where they go up to one of those playgrounds with the merry-go-round with the motorcycle and put the motorcycle wheel up against the merry-go-round, make it go really fast. Yes. It only happens in Russia. We've never done that. We just didn't have the powerful motorcycle. We only have like 50cc little motorcycles. And it wasn't mine, so it didn't matter if we were going to wreck it. All right. Any other questions? Comments? All right, that's going to do it for today. That's going to do it for this week. I will see y'all on Tuesday, and we'll start doing some cool graphs. Everybody have a good weekend, and thanks for playing.